Hello, this is Lesson 9, Double Roots for the Characteristic Equation. We will be looking at a second order equation like this one. It's homogeneous since we have 0 on the right. It's linear, and A, B, and C are constants. We saw that for this we can get a characteristic equation by letting y equal e to the rx. And that characteristic equation is a quadratic equation in R. What happens if that characteristic equation has double roots? Let's look at the quandary of having a double root for the characteristic equation. So we're going to be considering a times the second derivative of y with respect to x plus b times the first derivative of y with respect to x plus c times y equals 0, where a, b, and c are constants. This is a second order linear homogeneous constant coefficient ordinary differential equation. So we know that the solution space for this differential equation is two-dimensional. So there have to exist two linearly independent solutions. Let's call them y sub 1 of x and y sub 2 of x that can be used to generate all solutions. But let's suppose that this characteristic equation has a double root of lambda. So one solution then is y sub 1 of x equals e to the lambda x. But for that other root of lambda, you can't use y sub 2 of x equals e to the lambda x because y sub 1 and y sub 2 would not be linearly independent. It would not give you a two-dimensional solution space as its span. So the question is, what is another solution y2 of x such that y1 and y2 are linearly independent? Here's a fact about double roots to the characteristic equation. If lambda is a double root of the characteristic equation, then y sub 1 of x, which is e to the lambda x, and y sub 2 of x, which is x e to the lambda x, are two linearly independent solutions to that ordinary differential equation. And in that case, the general solution of the differential equation is a linear combination of these two. Y of x equals c1 times e to the lambda x plus c2 times x times e to the lambda x. We will see how we can get this second term later. But first, let's look at an example. Let's consider this problem. Solve the initial value problem, the second derivative of y with respect to x minus 6 times the derivative of y with respect to x plus 9y equals 0. And the conditions, y of 0 equals 1 and y prime of 0 equals 0. Looking at this differential equation and looking for solutions y equals e to the rx, we can see that the characteristic equation is r squared minus 6r plus 9 equals 0. This factors into r minus 3 quantity squared equals 0. So lambda equals 3 is a double root of this characteristic equation. So the general solution to this ordinary differential equation up here is going to be c1 e to the 3x plus c2 times x e to the 3x. Let's continue this example. So we saw that the general solution to the differential equation is c1 e to the 3x plus c2 x e to the 3x. The initial value problem had two initial conditions. The first one, y of 0 equals 1. Plugging 0 in for the x up here, we get c1 e to the 0 plus c2 times 0 e to the 0 equals 1. Let's remember that e to the 0 is 1. So this simplifies to c1 plus 0 equals 1. Thus, c1 equals 1. The second initial condition was on its first derivative. Y prime of 0 equals 0. To find y prime of x, we need to differentiate y of x up here. So y prime of x is 3c1 e to the 3x. We get that by differentiating this first term using the chain rule. And then For the derivative of this second term, we have to use the product rule and the chain rule. And we get 3c2x e to the 3x plus c2 e to the 3x. So now y prime of 0 equals 0 is going to give us what condition? Y prime of 0, plugging into this equation up here, is 3c1 plus c2. And that has to equal 0. And that tells us that 3 plus c2 equals 0, since c1, remember, was 1. And thus, c2 has to be minus 3. So now for the initial value problem, we have found what c1 and c2 must be. And so the solution to the initial value problem, y of x, equals 1 times e to the 3x minus 3 times x e to the 3x. Here is the graph of the solution to that initial value problem where the ordinary differential equation had a double root of 3. On the y-axis, we're going from minus 10 to 10, and on the x-axis, from 0 out to 3. And the solution of that initial value problem looks like this. Let's ask what happens if we look at similar initial value problems with the same initial conditions as before, but let's change the ordinary differential equation just slightly so that the characteristic equation of that ordinary differential equation has distinct roots, 3 and 3 plus epsilon. What we'll do is solve the initial value problem several times for epsilon equal to 1, 1/2, 1/3, minus 1/3, minus 1/2, and minus 1. When we solve those initial value problems with those values of epsilon, we get these blue curves over here, going from left to right. This first one is for epsilon equals 1. The next one over is for epsilon equals 1/2, 1/3. Then we have the solution to the initial value problem where the characteristic equation had a double root. Then epsilon equals minus 1/3, minus 1/2, and minus 1. If we look at this, it looks like we should be able to find out what the curve for the double root case is by approximating it with curves corresponding to distinct roots, where the distinct roots, 3 and 3 plus epsilon, get closer and closer to a double root by letting epsilon go to 0. And that's what we're going to do on the slides that are coming up. So now let's ask ourselves, when we have a double root to the characteristic equation, why does that second solution that we talked about have that extra factor of x in it? So let's look at this initial value problem, which involves a double root. The second derivative of y with respect to x minus 2 times lambda times the derivative of y with respect to x plus lambda square y equals 0. Looking at this differential equation, we see that the characteristic equation is r squared minus 2 lambda plus lambda squared equals 0. And this factors into r minus lambda equals squared equals 0. And so we have a double root of lambda. We'll also put in a couple initial conditions into this initial value problem. Y of 0 is 1, y prime of 0 is 0. So we have a double root lambda for the characteristic equation, and we want to find the solution y of x to this initial value problem. So here's what we'll do. Instead of looking at this initial value problem that has a double root of lambda, let's consider a slightly altered initial value problem where the characteristic equation has distinct roots, lambda and lambda plus epsilon, where epsilon is some non-zero number. So we'll have, in this initial value problem down here, two distinct roots. And so we can use the technique that we had before for finding solutions to that. So we'll find the solution y sub epsilon of x to this initial value problem, and then we'll see what happens as epsilon goes to 0, so that this problem with distinct roots gets closer and closer to the problem with double roots, a double root. So we're going to first approximate and then take a limit, secondly, as epsilon goes to 0. So initially, let's look at an initial value problem where the characteristic equation of the ordinary differential equation is this. So one root is going to be lambda, and the other root of the characteristic equation is lambda plus epsilon. And then we'll see what happens to the differential equation's solution as epsilon goes to 0. So the differential equation that has this characteristic equation we can write this way. And the function I'm going to call y sub epsilon. Y sub epsilon is the solution to this initial value problem, which involves constants involving epsilon here. The second derivative of y sub epsilon with respect to x minus 2 lambda plus epsilon times the derivative of y sub epsilon with respect to x plus lambda squared plus lambda epsilon times y sub epsilon equals 0. Initial conditions, y sub epsilon of 0 is 1, y prime of y sub epsilon, y prime sub epsilon of 0 is 0. Didn't say that quite right, did I? But close. The solution to this problem, since we have two distinct roots, is y sub epsilon equals c1 e to the lambda x plus c2 e to the lambda plus epsilon quantity times x, since the characteristic equation has two distinct roots, lambda and lambda plus epsilon. Continuing with our calculation, we saw before that the solution to that slightly altered differential equation was y sub epsilon of x is c1 e to the lambda x plus c2 e to the lambda plus epsilon times x. One of the initial conditions was that this function y sub epsilon evaluated at 0 had to equal 1. Well, according to this, if I plug in 0 for the x, we get c1 e to the 0 plus c2 e to the 0, and that's just c1 plus c2. So that first initial condition becomes the function evaluated at 0, which is c1 plus c2, has to equal 1. We also had an initial condition involving the derivative of y sub epsilon at 0. So the first thing we need to do is to figure out the derivative of the function y sub epsilon of x. Differentiate this function of x up here with respect to x term by term, and we'll have to use the chain rule in differentiating these exponentials. So what we get is the derivative of y sub epsilon at x is lambda c1 e to the lambda x plus lambda plus epsilon c2 e to the lambda plus epsilon times x. Evaluate this at 0, and we get for this lambda c1, and when we substitute x equals 0 in here, which makes this factor e to the 0 right here, which is 1, that second one becomes lambda plus epsilon times c2 equals 0. Our initial condition was that the derivative of this function at 0 equals 0. So we have two conditions on c1 and c2. This condition up here, this condition down here. So we need to solve those two equations for c1 and c2. It's an algebra problem that probably many students in junior high school could solve. And your answer will involve lambda and epsilon. It turns out that c1 equals lambda plus epsilon over epsilon. c2 is minus lambda over epsilon. It's easy to see that if we add these two together, we do get 1. And a short calculation can show that these two values for C1, C2 also satisfy this second equation. I'll let you check that in your spare time. So let's continue this calculation. We saw that the solution to the ordinary differential equation involving y sub epsilon was y sub epsilon equals C1 e to the 3x plus C2 e to the 3 plus epsilon times x. And we also just found out that C1 for the initial value problem has to be lambda plus epsilon over epsilon, and C2 had to be minus lambda over epsilon. So substituting those in up here, we get the solution to the initial value problem is y sub epsilon of x equals lambda plus epsilon over epsilon times e to the 3x. That's C1 times e to the 3x. And then C2 times 3 plus epsilon to the x is going to be minus lambda over epsilon times e to the lambda plus epsilon times x. Okay, so now we are going to take the limit. We have so far that our function y sub epsilon evaluated at x is this stuff over here. Lambda plus epsilon divided by epsilon e to the lambda x minus lambda over epsilon e raised to the lambda plus epsilon times x power. Let's manipulate this algebraically a little bit so we can see what happens when we take a limit. First of all, e to the lambda plus epsilon, that quantity times x, can be broken up using laws of exponents into e to the lambda x times e to the epsilon x. The rest of this we'll just copy down here. Okay, now going to the next line down, this stuff here is exactly what we have up here. And now we're going to rewrite it. We're going to put everything over a common denominator of epsilon. Okay, so here's what we have. We have lambda over epsilon times this exponential, and that's what we have here, lambda over epsilon times this exponential. And then we have epsilon times this exponential over epsilon, and that's here, epsilon times this exponential over epsilon. Then over here, we have lambda times e to the lambda x over epsilon with a minus sign here. And so here it is, lambda times e to the minus lambda x times this e to the epsilon x. So basically a simple calculation putting everything over this denominator of epsilon. Now, epsilon e to the lambda x divided by epsilon is just e to the lambda x. Looking at the other terms, we have this term, which is right here, minus this term, which is right here, divided by epsilon. Okay, so we now see that this fraction is equal to this fraction plus this exponential function. Now, if we look at this numerator, we notice that we can factor a lambda e to the lambda x out of both terms. And when we do that, we have lambda e to the lambda x times the quantity 1 minus e to the epsilon x over epsilon plus e to the lambda x, this term here. Now, if we look at this, let's consider what happens to 1 minus e to the epsilon x over epsilon as epsilon goes to 0. So we're going to look at the limit as epsilon goes to 0 of that quantity. Now, if you look at what happens as epsilon goes to 0, this numerator goes to 0, this denominator goes to 0, so we can use L'Hopital's rule. And since we're looking at a limit as epsilon goes to 0, we will differentiate the numerator with respect to epsilon and the denominator with respect to epsilon. When we do that, using the chain rule again, on the numerator we get minus x e to the epsilon x. This derivative in the denominator is just 1. So we're looking at the limit as epsilon goes to 0 of this. Now, as epsilon goes to 0, no matter what x is, e to the epsilon x goes to e to the 0, which is 1. So this numerator goes to minus x, this denominator stays at 1, the limit is minus x. So now plugging that back in, that as epsilon goes to 0, this factor up here goes to minus x. We get the limit of y sub epsilon of x as epsilon goes to 0 is minus lambda x e to the lambda x plus e to the lambda x. Now you can check by yourself to show that this really does satisfy the initial value problem that we started with that double root of the characteristic equation. So now I'm going to show what the two linearly independent solutions to that differential equation having double roots to the characteristic equation are. So let's look at the differential equation that we were looking at initially with double root. And now we have that y of x equals minus lambda x e to the lambda x plus e to the lambda x is a solution to this differential equation. Remembering the superposition principle for linear homogeneous ordinary differential equations, we saw that linear combinations of solutions to that differential equation are also solutions. A sum of solutions is a solution. A multiple of a solution is a solution to that differential equation, that linear homogeneous differential equation, L of y equals 0. Well, since we know that minus lambda x e to the lambda x plus e to the lambda x is a solution to this equation, and we also know that minus e to the lambda x is a solution, if we add those two together, we get that minus lambda x e to the lambda x is also a solution. And if we divide this by the constant minus lambda, which is the same as multiplying by a constant, we see that x e to the lambda x is also a solution. So let's consider the ordinary differential equation, its second order linear constant coefficient homogeneous, a times the second derivative of y with respect to x plus b times the derivative of y with respect to x plus c times y equals 0. Its characteristic equation is ar squared plus b times r plus c equals 0. Let's suppose that r equals lambda is a double root of that characteristic equation. Then the general solution to this differential equation up here is y equals c1 e to the lambda x plus c2 times x times e to the lambda x. Let's consider one more example, a trivial example having a double root. Let's just look at the second derivative of y with respect to x equals 0, this differential equation. The characteristic equation is r squared equals 0, so r equals 0 is the double root of that characteristic equation. So by what we have already said, the general solution to this ordinary differential equation is c1 e to the 0x plus c2 times x e to the 0x. Using the fact that e to the 0 is equal to 1, this simplifies to c1 plus c2 times x. We could have also solved this differential equation by just integrating it twice with respect to x. And if you do that, you will find that you still get this solution where c1 and c2 would have been arbitrary constants of integration. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.